Welcome everyone to today's CSIA Wednesday webinar series. My name is Colin Hammond and I will be your host today. From its start, CSIA was built on the principle of collaboration and with the goal to advance the industry of control system integration. In times of crisis, our members turn to the CSIA community as a trusted source for advice and inspiration. In line with this, we have begun this Wednesday webinar series. Our goal is to help our community manage, survive, and hopefully thrive from the current crisis. We plan to cover a wide range of topics on coping and leveraging the current situation and have SIs, vendor partners, and special guests present. For those of you who are unfamiliar with CSIA, we are a global nonprofit professional association with over 500 member companies in 40 countries. Our mission is to advance the practice of control system integration to benefit our members and their clients. Our vision is to ensure that manufacturing and process industries everywhere have access to low risk, safe, and successful application of automation technology. CSIA membership offers members access to resources needed to attain and exceed business goals. To highlight just a few of our many member benefits, the CSIA Best Practices Manual guides control system integration companies in the setup and running of a solid company. CSIA's business insurance program offers members an excellent insurance program for business owners, subcontractors, and more. The program includes members from all over the world enjoying the peace of mind that comes with CSIA insurance. Clients in all industries are now seeking integrators with a CSIA certification alongside ISO. They recognize CSIA certified integrators' commitment to industry standards and business acumen. As a result, being certified can shorten the sales cycle. CSIA Industrial Automation Exchange is the premier automation guide featuring system integrators and suppliers who provide industrial, manufacturing, and process automation solutions. For integrators and suppliers, it's a place to market their expertise. Clients will find white papers, case studies, capabilities, contact information, and engage in conversation directly with CSIA members. Please follow CSIA's online events calendars for all upcoming webinars. CSIA partner webinars are opportunities given to CSIA industry partners to address hot topic and demonstrate their expertise. CSIA business webinars features topics handpicked by CSIA leadership to help you run your business. You won't want to miss these opportunities to learn from the comfort of your own office or home. And for more information about CSIA, please visit our website or contact us at info@staff.controlsys.org or 847-686-2245. And at this time, I would like to introduce and hand it over to Jimmy from Schneider Electric, Jimmy Alvarez. Welcome, Jimmy.
Thank you. Thank you, Colin. Let me share my screen. Let me present.
All right, looks good, Jimmy.
I think everything looks good. Hey, thanks for having me here. Thanks for the invitation to attend this webinar. Hello to all the audience. Good morning to all of you. My name is Jimmy Alvarez. Actually, I'm responsible for the automation controllers product offering at the Schneider Electric here in the US. I have 20 years experience in the industrial automation business, working with different companies and having different roles. The objective of this session is to share with you a brief introduction about functional safety. The plan is to take you through the safety standards with a deep conversation around 13849-1. And finally, I will share with you the product portfolio that Schneider Electric can offer and a little bit about our key differentiators with competitors that we have in the market. By basic definition, safety is the state of being safe. You know, safety is the condition of being protected from harm or other non-desirable outcomes. There are other definitions like the condition of being protected from or unlike the cause, danger, risk, or injury. And companies that employ workers have an interest, and most of the cases are required in keeping the workplace safe. Job-related injuries are something that responsible employers avoid. They take the time and they use company resources to make sure that the people who come to work each day are safe. And there are many reasons to do that. And they do it because of hazards. That is, I will say, one of the main reasons. And there are different hazards, if you have seen, and as you can know, and there are different hazards in the workplace. From spills on floors to unguarded machinery and moving machinery parts, to electrical hazards, to chemical and gases like acetylene, propane, and others. And safety is also required to avoid accidents, which eventually may result, unfortunately, in many cases, in loss of human lives, production loss, penalties, increased insurance premiums, negative image for the company. So to be compliant with regulations and standards, that is another reason why safety is required. So in summary, and based on this, we can create a direct relationship between safety, productivity, profitability, and sustainability in our workplace, in our world. But then the next question is what to do and how we have and how to have our workplace safe, how to avoid accidents and protect the people. So protection systems have been around for a long time. Going back to having a canary in the mine and throw out the industrial revolution. So they are not new thing. Various stakeholders were involved in businesses, enterprises, owners, suppliers, consumers, community members, and workers. Usually the business owners held the most power because of their financial stake. While owners had the financial stake, the workers risked much more often their lives, as I just previously mentioned. But governments and industry groups stepped into helping workers to avoid injury and death. More recently, I can say that in the last 15 years or so, risk analysis started to enter the equation. Monitoring systems were put in place to protect people and equipment, and these systems were external to the basic process on control equipment. So, and it's how the concept of functional safety really was created. As a general concept, functional safety is the part of the overall safety of a system or a piece of equipment that depends on automatic protection operating correctly in response to its input or failure in a predictable manner. The objective of functional safety is freedom from unacceptable risk or physical injury or of damage to the health of people, either directly or indirectly by proper implementation, or one or more automatic protection functions called safety functions, which is a new terminology that we will be deeply covering during this presentation. It is important to mention that functional safety is achieved when every specified safety function is carried out at the level of performance required for each safety function is met. The definition triggers the following important definition, which is the safety related parts of a control system. And the safety function will always consist of a function, a safety input device, a safety logic solver, and a safety output device or final control device. This is a must, this is always. And I wanna comment here a little bit that I have seen in my experience in the market with different customers, talking about safety functions, mentioning about safety related parts, and they are not always meeting with this concept of the safety related parts. I have seen just an emergency stop, really safety product, but going directly to a standard controller and having the actuator as a standard contactor, as an example. And they are claiming, and they are trying to claim in some cases that there is a safety function around. Just by having standard products in many cases, in all the cases, it is not anything, there is not a meet, or they are not really meeting any standard for safety. They have an input, which is safety, but they may have a logic non-safety and an output and non-safety. If one of those pieces are not a safety product, is not rated safety, they are not really achieving any safety rated in their safety solution. Just as a comment, because I think it's important, and I have seen that, and you will learn what is behind of those safety components. So then the components in the circuit are referred to as the safety related parts of the control system, and the design of the safety function is governed by the specific safety standards, which we will cover during this session. So following with the presentation, the standard, I'm going to talk now about the standards, the safety standards, the functional safety standards. And the standard is important to let everybody know that provides safety requirements. The standards provide guiding, is guided by principles for design and integration of safety-related parts of control systems. So in terms of safety standards, and you can see in your screen, the 61508, the IEC or EN, and 61508 is considered a basic or an umbrella standard for functional safety. So it is a generic standard, it's a generic safety standard dealing with the functional safety of electrical, electronic, and programmable electronic systems, irrespective of the application. That is an important word here. As such, is the main standard on the functional safety of control systems. So from 61508, used as an umbrella, we can see other different standards based on different applications. And just by this presentation or this webinar, I will concentrate in the 13849, which is perfect, is applied to all the control systems, very applicable to the machinery. But it is important also to highlight 61511, which is mainly focused for process, and the 62061, which is also for machinery, applicable for machinery, but it is used in C, which is safety integrity level. So in reality, for machinery safety, we have two different standards belongs or coming under the umbrella for 61508, which is the 62061 by SIL and 13849-1 by performance level. And we will see what is the difference and how to differentiate each other. We will see that during this presentation. So, what is the difference? Let's start talking about the differentiation between process and machine safety. This, if you work in a high-risk industry, it is very likely that you have heard of the terms personal or machine safety and process safety. So these type of safety measures have similarities, but they also have significant differences that are important to recognize when protecting the workforce. So process safety focuses on preventing fires, explosions, and accidental chemical releases in chemical process facility or other facilities dealing with hazardous materials such as refineries and oil and gas and production installations. And machinery safety focuses on preventing employees from hazards, specifically coming from moving machineries. I will say that is the main differentiation, but both machine and process safety revolves around injury and hazard prevention, but on different scales. So then hazards and risks are different, but the risk reduction methodology is pretty much the same. So for both, we go through the risk evaluation, which can be a risk assessment, hazard assessment. So we have different type of risk evaluations. We have We go next to the risk management. After that, we do the design, the testing, the operation, and the maintenance. And the metrics are not so different. For example, as you can see, for 61511, they talk about SIL or safety integrity level, where we cover different requirements like reliability requirements, targeting of a hardware in terms of random hardware failures, depending on the safety integrity level. We also cover about safe failure fraction, which is the fraction of the overall failure rate of a device that may result either in a safe fault or diagnosed unsafe fault. We also include other terms like HFT, which is it stands for hardware fault tolerance. If we go to 62061, we added the claim limit, is how formally we call a safety integrity level limit claim or claim limit when we refer to machinery. You remember 62061, and it's when we started talking about probability of failure on demand per hour. We also added the diagnostic coverage, common cause failure, and other different kinds of requirements, but we'll touch some of them during this webinar. And now that we started thinking about these metrics, it is important to clarify that all these metrics are used to minimize the risk of hazardous events. So safety standards detail how to increase design reliability by identifying and eliminating systematic faults and increase hardware reliability, but by understanding random faults associated with type of components selected. So that's why it is important to use safety products, because when you try to see or get some of this data from standard products, in many times it is almost impossible to get it because it is not built to comply with safety standards. That's why my recommendation on the safety related components, if you want to build safety functions and you are talking about safety, go to standards and select safety components in order to get all this information. So we have the two standards that I already covered, right? Talking specifically about machine safety. If you recall, we have the 13849 focus on performance level, and we have 16061 covering SIL. Both address the functional safety of machinery and control systems. But I will say the two difference is that one will include other technologies than electrical, which is the 13849. While 62061 is only used for electrical and process sector. So that's why, in my experience, I have seen customers, and because 13849 is an international standard, I will say that 13849 is the most common or the most usual choice for many OEMs here in the US and those other countries out of Europe. Even in Europe, in many cases, I have seen some OEMs building machines trying to comply with 62061, which is good, right? But they use international standard. Now there are some harmonizations around the world. So the preference is to use 13849, which is, I think, the latest version was released in 2015. Going back a little bit, in 2011, when for those that maybe in the audience, if you remember, the safety standard 954, when we were talking about categories, this standard was valid until the end of December. Today, this is an obsolete standard, but it is important to recall this standard because that standard was at that time, and it is now the basic in the category portion for the 13849, right? EM 954 was replaced by safety integrity levels with 62061 and performance level by 13849. However, again, as I just mentioned, categories are still used. So there are not direct equivalent to safety categories, and they require additional information and calculations that I will show. But from here, I'm going to start talking about 13849, which is, as I just mentioned, the usual choice globally by the fact that it is an international standard. So this, in this chart, so we can see an example and summary of the requirements for EN 954, plus the addition or the additional requirements for 13849-1. So for Cat B, as an example, the requirements were to use basic safety principles. So we can then see how the system reacts to a fault conditions and the principle used to achieve safety. For Cat 1, as well as basic safety principles, well-trained components are required. As with Cat B, it's a single channel, so a single fault could lead the loss of safety function, and the principle used to achieve safety is characterized by the selection of components. The Cat 2, which is also included in this chart, it builds on Cat B and Cat 1 by using basic principles. However, now there is a functional test at suitable intervals. So the loss of the safety function is detected by the test, and safety is achieved mainly by a structure. However, now we can see additional requirements, as I just mentioned. We added, so as you can see, they were added 3 different requirements or 3 different components to achieve with 13849. One is what they call the mean time to dangerous failure. The other one is the diagnostic coverage, which simply put is the ability of the system to detect dangerous failure. And finally, the common cause failure or a systematic fault that could affect both channels in a redundant system. So these 3 components were added at that time, and with categories plus these 3 different components built the new 13849. And some of the questions that I always get is why we didn't continue with 954. And I will say the general answer is because of the technology. So 954 was mainly built and based on the mechanical components. But at the moment when we were started seeing controllers with safety, drives with safety, soft starters, so more technology, chip-based technology products, the EN 954 were becoming obsolete, and in many cases were unsafe. That's why the 13849 was released as a new standard, mainly because it considers these 3 different requirements that covers the new technologies in order to really have a phase or a more secure and safe safety system. So let's talk now about these additional requirements a little bit more in depth. So this is the summary of the 3 additional components, as I just mentioned. The mean time to dangerous failure. This is the portion of failure modes that can lead to failures that may result in hazards to personnel, environment, or equipment. So it is the calculation in a simple way. It is the calculation of how often a piece of equipment or safety system fails in a way that threatens the safety of workers. So this data is typically provided by the manufacturer. I will show you a summary in the upcoming, in the following slides when you can see all of the details, but it is important. MTTFd typically is provided by the manufacturer in different ways. So if you don't have the MTTFd as is, typically manufacturers provide other data that can be converted to have the MTTFd, which is a requirement for the math calculations under 13849. So MTTFd, the mean time to dangerous failure, is given in 3 different levels. As you can see, the low, medium, and high. It goes through different years. In terms of the failure, you will see theoretical figures quoted in some cases of 3,000 years in your calculations. But typically in calculations, these are capped to at 100 years. So the diagnostic coverage, this defined as the ratio of detected dangerous failures versus all the dangerous failures. That is the difference, the detected and versus the detected and non-detected. It quantifies the ability of a system to detect dangerous failures. That is why we have it added in the 13849s. So as you may know, there are two different types of failures. These are safe failures and unsafe failures. Safe failures is where there are no safe consequences due to the failure. An example of this is a contactor, simple contactor, failing with the contacts open. So in this case, there is no power is applied to the device that it is switching. An example of an unsafe failure if when the contactor welds together. So even if the control voltage is disconnected, it is possible that the power is still applied to the device. So this is one clear example of these detected and not or safe and unsafe failures. So the diagnostic coverage is given in 4 different levels. As you can see, the known, low, medium, and high. And typically it is a percentage. We will talk more a little bit about it, but it goes at a minimum of 60% up to 99%. The definition of the common cause failure, which is a single systematic failure that can lead to the failure of both channels, so are considered to be really a common cause failure. Common cause failure occur when multiple, usually identical, components fail due to shared causes. These typical examples can be an impact, vibration, temperature, so in contaminants, miscalibration, improper maintenance, all of these, but typically in the environment exist. So typically there is a table in the standard that applies a scoring to method or elimination of avoid a common cause failure. Again, a score of 65 or above is required to the common cause failure. As I just mentioned, I have this table. I think this is a very useful table for quick reference. This is a summary of the basic requirements of this 13849, not including the category. This table includes a requirement. It explains what it is, how it is acceptable, how it is measured, and how we can get this information. So it is important to understand if you are designing something under 13849. So to really have a good understanding on this, again, more information is under this standard. So continuing with the presentation, now let's talk about the implications. As we just mentioned, and as we just learned, 13849-1 encompass more parameters to be considered based on reliability and time. So, but there is an important step, in the safety life cycle, which begins with the identification of a risk or hazards. There is an international standard for this, and it is typically used, and it is the 12100 2010. That is of safety of machinery. We talk about general principles for design, and it includes the risk assessment and risk reduction. So this standard specifies basic terminology, principles, and methodology for achieving safety in the design of machinery. So it specifies principles of risk assessment and risk reduction to help designers in achieving this objective. So all of these principles are based on knowledge, it is important, and experience of the design, and use, incidents, accidents, and risk associated with the machinery. So risk assessment criteria is defined and mapped to required performance levels. Estimating risk is evaluating many aspects, including severity of consequences, what are the chances, and what is the frequency of exposure. So severity is important, and we will cover that in the following slides. It's about how bad can be the injury. What is the frequency? It's about how often is the worker is exposed to the hazard, and the avoidance and is about how likely will avoid to be exposed to that hazard. So risk assessment really evaluate the potential hazard in order to determine the required performance level. As you can see in the graph, the three components under 13849 in nutshell is around severity, frequency, and avoidance. And this graph, this mapping that we will cover later, it includes different levels of severity, frequency, and probability of avoidance that really take me to the different levels of performance level. As you can see, we have 5, and all of them has, provides different level of safety or risk level, as you can see, from low to high. So this is the standard flow chart for risk assessment, right? It typically starts with the machine characteristics or limits, the machine and the setup that assessment is for. As a comment, if any part of the machine, process, or energy source are modified, the risk assessment may need to be redone to ensure the proper risk reduction for the new configuration. So machine characteristics and limits is important, is the first recognition of this process. And then we go to the hazard identification, assuming that there are no guards in place. So, and is when the person of the team really start doing different task hazards oriented, and they analyze the terms of severity, frequency, and avoidance in order to determine the appropriate product level requirement. Then we go to the risk estimation, and again, here is when we do this, the severity, frequency, and probability. And the risk evaluation is when we apply the mitigation hierarchy. We will talk a little bit about it, but it's specifically about the solution, which is based on when the structure that we just reviewed, the reliability and monitoring in order to confirm if the performance level is achieved. It is achieved, it is a tolerable risk, then we go to the next hazard in the machine. And if it is not, we need to come back and to start doing a deeper analysis in the hazard identification. Very simple process, but again, some recommendations is that can be a team-based is the best, can be applied to task hazard oriented. It's important to do the analysis in order to really determine the appropriate performance level. There are different risk assessment models in the market today, right? And again, 13849 is just one of them. And as I just mentioned, it's international, it's harmonized to many, I would say almost all the standards globally today. But if you are using one of them or the other ones, it's okay. You know, I think at the end of the day, you choose what is suitable for you, what you feel comfortable with that. So if you are not shipping machines out of the country, if you are shipping machines here locally, and if you are doing ANSI, that is fine. If you are ANSI RIA, which is more for robots, that is fine. If you have the necessity to ship machines to Europe, for example, where maybe 62061 is better for you, but you can use 13849 if that is better for you, if you are more comfortable, performance levels are also acceptable in that continent. We have been talking about risk assessment, but going back a little bit, I think to me it's important to clarify some key concept or basic concept, right? It is important, the risk evaluation and different models of risk assessment, but the concept is very key. It's about what is hazard, right? What is a harm and what is a risk, right? As I define here, hazard is a potential source of harm. Harm is really a physical injury, and risk for safety is a combination of the severity of the harm and the probability of occurrence of that harm. So if you put that in different components, as I just previously mentioned, is around the severity, the frequency, and the avoidance. And we will talk about this. So this is the mapping that I just mentioned. This is the combination. This is the graphical that I show here. But the severity, I have two different components or two different levels. I have the slight which is something that can be considered reversible, right? And the other, an upper level, which is serious, which is the S2, which is the non-reversible. And we can have maybe, you know, you have an injury in your finger, an injury in your hand, an injury in your leg, which in many cases might not be reversible, but maybe something in your finger can be reversible. When I have two different levels, that's one example of it. Frequency of exposure, maybe frequency 1 is a seldom or short time, right? And frequency 2 is maybe the frequent, is a big frequent, is really high frequent, and maybe a long exposure. And with the probability can be, which is avoiding of the hazard. When the big one is really possible to avoid the hazard, or really scarcely possible to do the hazard, which is the probability 2. So this is an informative information come from one of the annex in the standard, but typically that allows suppliers and users to create their own terminology. So the one that I just explained is just for the purpose of the explanation. But again, when you go to the standard, it really gives you different and the opportunity to do your own groups of severity, your own levels of lower and low and high level of severity, frequency, and probability. This is an example of that typical risk estimation, as you can see, and the severity on the serious slide. And this is just a table from ANSI, just to give you an example. I took that from there. And they put, for example, frequent, non-frequent, likely, not likely, and it explained the criteria. Again, this is based on the risk assessment, and typically the expert, typically a person or people in terms of knowing about the standard, having a team base with the people, the users of the machine, maybe also including the people from the manufacturer of the equipment, or maybe the system integrator that can participate in the design of the control can be part of this risk estimation definitions. I will say that is important because it really triggers the level of performance that we will build based on 13849. I also included in this presentation an example. This is a mechanical automatic press. As you can see, this person typically, you know, he moves his arm. He puts something in the middle of this, and typically the press goes up, goes down, and they do that maybe 10 times per hour, and consider that as an example. So how severe could be the injury? Maybe it's really serious, right? Because if something is wrong, this person can lose his arm, right? What is the exposure of the hazard is frequent, right? 10 times an hour is too much, right? And maybe it goes to E2, and consider the hazard can be avoided, maybe not, because it's part of his job. So then immediately when you see it goes to the highest level of the performance level, right? When we have the higher level of severity, the higher level of exposure, the higher level of probability, it takes me to the performance level E, which is typically, if I would go to 62061, it takes me to SIL 3 level, which is the highest level of safety. So when applying safeguards, the approach of the selection of appropriate measures is addressed through a well-recognized hierarchy that called hierarchy of measures, or by many standards are the hierarchy of controls. So the explanation of this approach deserves, believe me, a topic all on its own. And well, we don't have time during this session. Then in summary, the concept of this approach is that different type of risk mitigation processes provide different levels of effective risk reduction. Therefore, the higher risk, the more we focus on applying more effective risk reduction measures. So the philosophy, a warning label would not be effective risk reduction measure, typically, and of itself for the reduction of high risk hazards. So as supported throughout this hierarchy, right? So typically when you do the risk assessment, you have all of these different measures of risk reduction. As you can see, in the third level is where we have engineering, guards, devices, layers of safety. But below we have some done by design, right? Some others just by putting a hard guarding and that's it, right? We don't have really having people having access to that area and just put it a guard, that's it. We avoid too many, we can avoid the hazard. But in many cases, we had people, working with those hazards, which maybe the level 3 might be applied. Other different levels, like implementing administrative controls, like training, might be enough. Another maybe using the PPE, like using only goggles or gloves. That's gonna be good. So again, to me, this is a specific topic, special topic that we can cover. But again, just to let you know that as part of the risk reduction, we have different levels of risk reductions. So once we have the performance level required, right? Once we completed the hazard assessment, when we are sure that we are done, completed, then the next step is to build the safety system to achieve that. And as we learn, we take the international standards here. This is what we are covering, the 13849. And typically what we have to start is with the category structure and the 3 additional components. What is that, right? First of all, for you that might be familiar with EN 954, these categories are really the EN 954. We have Cat 1 and B, which are single channel, single fault, can lead the loss of the safety function, right? As you can see, we have the input, we have the logic, the output, but again, a simple fault can lead the loss of safety function. The Cat 2 introduces a test element, and you can see, and this test detect whether any fault are present. A single fault can lead to the loss of safety function between these tests, while Cat 4 and Cat 3 are dual channel or redundant. The only difference is the level of diagnostic coverage that it requires in order to detect accumulation of force, which is what we have in Cat 4. But if you can see, this is the structure. We, again, even though EN 954 is obsolete, 13849 took that as the basic concept of the structure of the categories. An example of this electrical, I put this in an electrical example. The diagram in the left shows a simple single channel safety circuit. And in the one in the right, you have a dual channel input output with monitoring. Right? As you can see, we have redundant component, we have testing, and what we typically do is that a fault can cause a loss of the safety function, the one in the left, but the ones in the right, the faults might be detected or will be detected in time to prevent the loss of the safety function. This is just to put you more like a realistic electrical diagram when we build single channel Cat B or single channel Cat 4. Then we move to the other 3 different components. We collect the data, as we just mentioned, from the vendor, from the manufacturer, the MTTFd, and we also get the diagnostic coverage. Remember, the common cause failure is also something that is based on the experience, and really one of the annexes for the 13849 can give you a guidance in order to meet the 65 points. So when you open the 13849, the 13849 really takes you through how to do the calculations, how to get the data. If you get the data from manufacturers in one way, what are the typical formulas to convert it to MTTFd? So the same for diagnostic coverage. But one of the good recommendations that I can add, that I can provide you is today in the market, you can find different safety software tools. And one that I recommend, and I will show you in the next couple of slides, is the one that we call SISTEMA. SISTEMA is a free It's a free, really free, free software, and you can download it again from a link, and we'll show you that, and that will help you to avoid to go and do your own math that can really take you time, and you can get it from there. It is important to know how to use it, to know how to get the data, put it there, but it can take you to the performance level requirement easy and very quick. So when you have this, all this data, I like, this is the graph. And I like the graph because it really exemplifies and really take you through the really performance level, and it tells you you hit to the performance level required or not. As an example, as you can see, you have here, I'm going to point here, you have the performance level requirements. You have the A from A to E, the understanding that A is the low or the lowest, the performance level E is the highest, right? And this is the structure, the category, and we go from Cat B to Cat 4. In many cases, we have duplication. We have two different, Cat 2 in two different levels, Cat 3 as well, right? Because why? Cat 2 can be this basic structure to achieve performance level C, but if you have a Cat 2 structure, and if you are diagnostic coverage in your system, with Cat 2 architecture, you can also be able to achieve performance level D, which is good. In terms of engineering, that means money, that means the cost of the product, that means wiring, that means engineering. It is important for you to understand. So if the system is asking me for performance level D, so how can I get to performance level D? How can I get to performance level C? Can I get it by using a Cat 2, or do I really need to go and get a Cat 3 or Cat 4, right? Those are the different evaluations and solutions that you can do that can really make your safety system at the lowest cost, but also achieving different performance levels. Again, as an example, well, first of all, we have the structure of category, diagnostic coverage, and reliability. For example, if I have a hazard which is asking me to achieve performance levels, let's put this performance level D. As you can see, there are 3 different ways to get performance level D, right? I can do it with Cat 2, Cat 3, in 2 different ways, Cat 2 and Cat 3 as the architecture, but I can get it with different diagnostic coverage. I can get it with the highest diagnostic coverage in Cat 2, or I can do it at Cat 3 and I can use a component that can give me not that high of diagnostic coverage, and maybe can be even rated at from 30 to 100 years, right? Or I can take one from 10 to 30 years, right? But I have to have Cat 3 and high diagnostic coverage. This is just to show you different combinations and how I can achieve different performance levels. So this is the tool that I just mentioned to you. This is free. It's not from Schneider. The database that IFA has on the SISTEMA software, it has a database for all the manufacturers of safety components, right? It's for machinery. It is important. It's not for process. And it's very easy. It has tutorial on how to use it. It's recommended by TUV. If you go to this link, you can download it. It's my recommendation, do it. And it's gonna take you through a process, but it asks you for information, right? Again, the Schneider Electric Data Library is included, is here. And it has all the Schneider Electric's latest, with the greatest and greatest safety product. And it is important, is the maintained, and it was developed for a Germany company. So use it. My recommendation, you're going to reduce your time and effort in order to work on this and to really understand if, or make sure that if you are going to achieve with that system and with those components, the performance level that is required based on your hazard or your risk assessment. So now, talking about our products for Schneider, it is important for the audience to know that we are very good in terms of the components that we offer in the market. We know we are very, very well recognized for process safety. We have products and we are the #1 in many cases for with Triconics, for example, or with a very, very process safety orient applications. But I wanted to let the audience know that don't forget, our products and our controllers are really good and can be used and are approved also for machine safety. We have safety inputs from safety interlocks, safety light contains, safety switches from non-contact and contact, emergency stop, safety limit switches, cable pull switches. We have a variety with different technologies of safety inputs. Remember, it's part of the functional safety. You have to use safety components. And you have safety logic in different levels. We have the safety relays, modular safety relays, safety PLCs with integrated motion. And we have, and something that I will talk to you is about the EPAC for a standard safety and process safety control. Which is pretty good. I'm gonna cover a little bit, I'm gonna talk a little bit about it. And also important, we have safety outputs from safety contactors, going through the safety drives, and also through the safety motion control. I will say use it again, and we have the people, we have the knowledge, we have the product, we have the tools in order to go through 13849, if that is the one that you are going to use, in order to build your safety solutions with Schneider Electric. Also, talking about the EPAC, one of the key differentiators is that the EPAC, the M580, I will call it a common safety solution, because it can be used for process and machine safety, right? For machine, we can comply with all the standards and we can work with all of these components, input, output. Our controller is also enabled with chip safety, which is one of the trends and more is recognized in the market today. So it is enabled with chip safety. And also, the MC safety pack is SIL 3, the SIL 3 PLE, if you remember. So it can achieve up to SIL 3 PLE, again, SIL 3, SIL claim limit 3 by 62061, SIL 3 by 61511, and PLE by 13849-1, again, for process and machine safety. It also compliant with specific standards for fire and gas, emergency stop, and some BMS. When I talk that it is for process, it's a real process, right? It can be suitable to use for process safety application. And one of the key differentiators that we have in the market is that it does safety as a standalone and it supports high availability with redundant CPUs. Something that is unique in the market. I really encourage you to use it. We have other different values. And also, this is the safety IOS, the redundant safety and power, the power supply, and the X80 IOS for safety and non-safety in the same engine, and also the control expert, which is where you can do your programming using different languages like standard, function blocks, and ladder. I think that is one of also the key differentiations that we have in the market. This is just for your reference for process and safety in one controller. Something that I have seen competitors that cannot do this, take advantage of it, same controller from different applications. And also, as I just mentioned, SIP safety, open with conformity with ODBA that can support other SIP safety products. And it is important just to remind you or to put you in the concept of the Triconics and F580, right? And Triconics very, very focused in critical processes when we are leaders, and also discrete when we have the F580, and the high available process when we have both, right? Again, take advantage of it. Those are really cool products, and we have again the knowledge, the experience, and the people to support the product and the technology to support your safety systems. In summary, safety systems encompasses parameters to be considered based on reliability and time. Safety systems in machinery are rated in SIL by 6261 or performance level by 13849. Manufacturers publishes the SIL and limits, performance levels, and all of these values when there is a safety product. 13849 is the most common. Why? Because it is international standard, is what I've seen in the market. And Schneider Electric has relevant safety data for safety rated components, right? Safety components for both process and machine. And we also have application notes, and we can take you through all of these different tools that we have in order to implement your functional safety. So we are also almost on top of the time. So this is my name, this is my email. I don't know if we are going to have time to answer questions, but I can answer your questions. Please contact me. Again, Jimmy Alvarez. And with this, I'm done calling. If you want to have some final comments, we're going through some questions. We have a couple of minutes, but this is my presentation. Thank you for your time today.
Thank you, Jimmy. So we had a question, will the presentation be available for us after the webinar? Yes, this will be recorded. Are we going to see Schneider's safety PLC today?
So, well, we talked a little bit about it, right? We talked about the M580 a little bit. I think, and just to let you know that it supports also discrete applications, not only process. And I think we covered that topic. If you want to know more, if you would like to know more details about our product offering, please send me an email or give me your email and I can send that calling. So I will be very glad to do that.
All right, thank you, Jimmy. Well, on behalf of CSIA, I would like to thank all of those attending. I'd also like to thank Jimmy for this informative discussion. A recording of this webinar will be available for viewing probably by the end of the week. And please visit the CSIA website to view this recording or a past webinar you may have missed. And that concludes our program for today. Thank you, Jimmy, and thanks to all of those attending. Have a good afternoon, everybody.
Thank you.